What did I define quality as when we were together yesterday? I mentioned it.
Percentage of basically like the composition between fluid and gas.
Then your quality is quite close to zero, because quality is a measure of mass, not of volume. Okay, so volumetrically, you'd look at that and go, oh, it's 50% vapor, it's 50% liquid. Well, the liquid is more massive in this container, so the quality is quite low. Once you get to about 50% quality, you start talking about droplets of water suspended in air. So I think that's just interesting diagrammatically, because it's not necessarily intuitive how you would think quality is measured. So here's an example of a question. 65 kilograms of water is contained in a tank with a volume of 1 meter cubed at 300 degrees C. So you've got an overall volume, you've got a temperature, and you've got a mass. So mass and volume, you've got a specific volume, and you've got a temperature. So these are two independent intrinsic properties, so that we have affirmatively defined the state of the substance. And the question is, what's the state of the substance? What's the quality of the substance? So that's the question we'll move to after we've talked a little bit about quality. We represent quality with the letter X. It's not a mistake. And it represents the mass fraction of gas, so the vapor part of a substance, pure substance, divided by the overall mass of substance that you have. Okay, so that's our formal definition. It looks like the ratio of two lines if you're doing things graphically. It looks like the ratio of different numbers if you're doing things as a calculation. If the quality is zero, that means it's a saturated liquid. So if the quality is zero, all of the substance is liquid, and if you cool it anymore, it'll become subcooled. If you add any energy, it'll become a mixture. The quality will rise. So it's saturated liquid. If the quality is 1, it's a saturated vapor. If you remove any energy, some liquid will condense out, or if you increase the pressure, some liquid will condense out. If you increase the energy, you'll go into the superheated vapor. Right? And quality only exists between those two states. So if you have a compressed liquid, you don't have a negative quality. If you've got a superheated gas, superheated vapor, you don't have a quality of 1.2. It's bounded by those terms. So quality is a term that only exists within that range. And when you think about it, if you say the quality of steam, right, and you're trying to generate power, you would say high quality steam, a large number, is steam that's got lots of energy, we can use it. Right? Low quality steam is steam that has liquid water in it, it's got lower energy, it's less useful. So quality as a term, as a word, kind of makes sense. To calculate it, so this is if you're using numbers, okay, you can take some property, denoted here as phi, and if we know what that property is at the saturated fluid state, and we know that what that property is at the saturated gas state, okay, so this is the property value at the saturated fluid state, this is the property value at the saturated gas state, vapor state, and of course, liquid state. Notice here this is for example, Hg minus Hf, which on our tables is listed as, I think it's HFG, might be HGF, right? But your table specifically lists for enthalpy H and for entropy S, a HFG and a SFG figure, so you don't have to do this subtraction all the time. I kind of mentioned that yesterday when we were talking about tables. So if you know the value of the property, and then you know what the value would be if it was a saturated fluid or a saturated gas, then you can calculate the quality X. And this is true for all properties phi. Okay? So in our question case, we've got specific volume. So knowing the specific volume, we can calculate the specific entropy. We can calculate the enthalpy. We can calculate the internal energy using the same formula. We just make a different term the subject. In this, X is the subject of the formula. If we make phi, where phi is any of these, the subject of the formula, then it always works. I've just put a little note here. If you know the pressure and or the temperature, that doesn't help you calculate X, because quality exists only when you have a saturated mixture. If you have a saturated mixture, you know the pressure and temperature because they are not independent at that state. So this is what I was saying before. If you use some property, phi, to calculate X, then you can calculate some other property, theta, using X just by rearranging the equation. I'm heavy on concepts. I didn't actually present this equation last session because I just derive it each time I use it. And people said, well, what's the equation? So that's the equation, if that helps. So let's try and answer this question. 65 kilograms of water is contained in a tank with volume at 1 meter cubed. What is the state of the fluid? Excellent. Good, good. So we're at 300 degrees C, which is there. And so one of our independent intensive properties is temperature, which is excellent. The other independent intensive property I propose is specific volume. Excellent. What's the formula for specific volume? What's the formula for any specific property? Excellent. Good. That property divided by mass. We've got the volume. We've got the mass. We're going to get a small decimal. All right. 0.015. Excellent. From this we can observe that 0.015 is more than 0.0014, this property here, this value here, and it's less than 0.021, right? So because it's between those two properties, the quality, the substance will have a quality, okay? If it was more than, so say, let's just take a different hypothetical case, right? Say you got a volume of, a specific volume of 0.04, right, meters cubed per kilogram. What would that indicate to you about the substance? Cool. That it's a superheated vapor. So if it was saturated, it would have a volume of exactly this, specific volume, of exactly that. If the specific volume is greater than that, then it's a superheated vapor. So we haven't changed the temperature, but we've just rarefied it a bit more. Remember, superheated vapor means if I compress it just a little bit, or if I take a little bit of heat out of it, it's not just about to condense. Okay, saturated means it's just about to condense. That's true of all of the properties. So you see that the UF properties are smaller than the UG properties. So if you have some property, pressure or temperature, and you're given a UF, and it's between those two values, you're dealing with a saturated mixture. If it's less than the value under UF, then you're dealing with a condensed or compressed liquid. If it's greater than the value on the right, you're dealing with a superheated vapor. And that's true also of enthalpy H, right? The smaller numbers on the left, the bigger numbers on the right. It's also true of entropy S. The smaller numbers on the left, the bigger numbers on the right. If you've got a number bigger than the number on the right, superheated vapor. Sorry, what I'm writing on is rotated with respect to what you're writing on. Superheated vapor, compressed liquid. I want to try and make that association directional because that's how you'll see it in the charts. Cool, so let's get rid of that. So because it is, get rid of some markings, because it is greater than the number on the left and less than the number on the right, it's in the saturated, it's in the mixture range, okay? And indeed, we said X equals theta minus theta F on theta G minus theta F, all right? Theta for us is now specific volume, right? That's what we're dealing with. The specific volume that we have, 0.15385 minus the value if it was saturated fluid, 0.001404, divided by the value if it was a gas, 0.02168, minus the value if it was a fluid, conveniently written above, x equals that's my calculator sound. I agree. Who's that? Excellent. Well done. Caramel Freddos today. It's about being fast on the keys. I had it written down. So, it can be represented as a number between 0 and 1 inclusive, or it can be represented as a percentage, 6 to 1. Excellent. Everyone comfortable with quality? So that means in some container, in this particular container, all right, so we've got some cube container, it's 1 meter cubed, I imagine it as a cube, all right, there is some small liquid level or liquid droplets in the air at this kind of quality, all right, that much is gas or vapor, and this much is liquid, such that the mass fraction is 70% of the mass of H2O in the container is a gas. Excellent. Just a note on quality. Quality will be specified with turbines. So when you buy a turbine, it'll say that it can't handle qualities below 90%, 95%, something like that, right? Because turbines are fast spinning blades in a gas stream, they expect gas, and vapor is a gas. So don't think of steam as being little liquid droplets. It's not. That's what we commonly think steam is, but steam is just like air. It's clear, and it's without droplets. Once you get low quality, you can start damaging your turbo machinery. Okay, so we care about the quality of our steam. Liquid water transmits heat much faster than vaporous water. So heat exchangers, you want some liquid in there. Turbines, you don't want any liquid. So there's some implications, but we'll just do calculations with quality. Are there any questions? That sounded like a question. No. Were there any questions about quality? Good.